Crazy wind the other day, huh?
Oh, it is really windy. Oh, hey, I wanted to show you this. I guess I can share the screen now. I want to. How do I do this? It's like if I had one more person, I could make you larger. Why can't I make it larger? When I have the whole grid, I can make it larger, but now I can't have the grid. That is so weird.
You want me to call in on my phone too?
That is, I thought I could do that. It's always nice when you have bigger faces. Oh, well, whatever. Did you guys see this? That was a pretty impressive hurricane for November.
Yeah.
Of course, way the hell south.
I believe it is the latest Category 5.
Was it a Category 5?
Yeah.
Yeah, man, just hit it.
It was.
Yeah, that was an impressive storm. I'm sure it did a lot of damage in Nicaragua. I mean, just looking at the convection flare-up on the sides, it's pretty amazing. And actually, if we go back, I don't know, maybe even further, it was a great, look at the size of that eye.
Jesus.
So watch this. Did it hit as a Category 5?
No, it went down to a Cat 4 right before it hit. So
I find it just amazing how what's been going on in the tropics this year. I don't think I understand fully what's going on. We can go maybe over here. Oh, there's OLR. I meant to do STA. It's not like it's super above normal in terms of sea surface temperature. I mean, that's fairly close to normal. I just don't understand. It's been something weird this year. You know, they talked about it the 30th named storm compared to 2005, which had 28. The only thing is, do you remember at the beginning of the season, Jacob, you may have been following this, they were naming a lot of stupid crap. I don't even know why they were naming some of these things. They had like 4 storms that they named, and I was like, what? You know, a couple extratropical. One was like near Portugal. Like they were naming everything. So it's a big season. I'm not sure if 30 is as legitimate as it even was in 2005. So, but nonetheless, that was a big late season storm. So it is pretty something. I guess that is the place where it would be. Is that it now, or is there another one out there? No. Let's just for the hell of it. Model doing anything? Atlantic. It doesn't look like it's doing much of anything. It's so this time of year, it's obvious that we could not get it further to the north. It has to be way to the south. Now look at that. That's a big storm. That's forecast. Well, that's way far, but it's still interesting. But that's not tropical, right? You can tell this is not tropical, right? Because you have significant cold advection behind this thing. Mm-hmm. That's just a really big storm system. By the way, I don't know. You guys should be taking forecasting. You would think you'd want to take forecasting with me all the time. Or are you taking it with Ron, Nick?
Yeah.
Oh, you are? Okay. How's that going?
It's going pretty well. He was talking about a lot of different things with kind of how the SPC is issuing watches, I guess at least recently, how possibly they could be using just the tornado watch to at least maybe bring up a little bit of hype. It's kind of interesting. He's got an interesting opinion on it, but
Oh, that's interesting. Yeah, hype is so dangerous.
yeah,
But
and
there's the next week, right? There's not that. I've been talking about this snowpack developing in the northern plains. Obviously, it doesn't look like there's going to be much of a snowpack. So we're not seeing any signs of winter into December. That's always sort of disconcerting. I mean, I don't know what it's going to be. There's a lot of snow out in the west, but oh well. Anyway, that's enough of weather. Let's go to our book. Let us go to page. I told you I wanted you to go, and we're going to skip this next thing. We'll start that next Thursday. And we wanted to go to page, what's the one that I wanted you to look at? Continuity?
Yes.
Inference of the vertical motion field. I think that's what I had you do, right, on page 293? So I'm just going to kind of go up here. Let me get out my Epic pen. Anybody else have Epic pen? Are you using that?
Yes.
Yeah.
Isn't it great to have that with the stylus? I just think it's really awesome. So
It's useful, yeah.
it really makes a difference to me. Okay, so here's what we've got. So I'm going to read through this together. The vertical motion field cannot be predicted on the basis of Newton's second law, but it can be inferred from horizontal wind field on the basis of continuity equation, which is an expression of the conservation of mass. Okay, so in a system where we consider a parson, you have the conservation of mass, which is known as mass continuity. Okay, now we've drawn the picture as that little tube of water coming in, going out, right? So that's how we kind of need to think about this. So it says air particles expand and contract in response to pressure changes. So what you need to consider is I have a container, and I'm going to make that container three-dimensional so that you understand that there is a three-dimensionality to it. Okay. And so that you're almost thinking this like a column of air. Okay. And what I'm saying is that the volume, the change in the volume, is only related, or I should say, is accomplished by changing external pressure or internal temperature. Does that make sense? If we change the external pressure, do you agree that this what do we call this? Not a cube, it's this three-dimensional volume, rectangular volume, will expand or compress depending on what the pressure is doing outside. But we can also do that by changing the temperature of this column, right? But the point is we can't do it by a forcing. So what I'm saying in this scenario is if I were to do something to expand the walls out, maybe something like this, right? I'm going to expand the walls out, and I'm going to do the same thing with these walls in the background and foreground. Okay, what would that do to the vertical distance is I would cause this compression. So imagine that I did something that in a square, in some sort of a, I don't know, I guess we could consider this to be some sort of a like an infinitely small slab, just a square. Do you agree that's just going to be an area? And we're going to stretch that area out, and that's going to cause the column itself to compress from on top. So it says air parcels expand and contract in response to pressure changes. In general, those changes in volume are of two types. Those associated with sound waves, in which the momentum of the air plays an essential role. And we're not going to worry about sound waves. And those that occur in association with hydrostatic pressure changes. When the equation for continuity of mass is formulated, and now they say something interesting. They say these are going to be in X. We always said coordinate systems would be X, Y, Z. But I'm going to use X, Y, P. And what we're saying as a pressure is the vertical coordinate. That is you understand that, right? When we look at soundings, we don't usually care as much about height as the vertical coordinate, but pressure. Now, there are other vertical pressure coordinates. Do you guys know either of those two? Anybody? What are other vertical coordinates often used in meteorology? There's two other important ones. There might be more. I'm just not thinking of them now. Jim, do you know?
Geopotential heights?
We're going to assume that Z is geopotential
Okay.
height. Okay, so yeah, you would be technically, capital Z is really more correct. Sometimes we use theta as a vertical coordinate. And sometimes we use sigma coordinates. Does anybody know what a sigma coordinate is? Have you ever heard that? Sigma, which is a very cool coordinate, is actually pressure divided by P naught. So what would, on a sigma coordinate, what would the bottom be? The bottom would be sigma equals 1, because the pressure is the surface pressure. What would it be at the top?
P plus, or P0 plus P.
It'd be, I mean, at the top of the atmosphere, it bounds to 0 because you'd have no pressure.
Right.
So your coordinate is between 0 and 1. When you look at models, they'll often use sigma coordinates to determine where they're going to be.
They're normalizing it.
Yep. Okay, so there you go. I just wanted you to know a little bit about that stuff. Okay, so
What's
those
theta then?
Theta is potential temperature. So use vertical.
Oh yeah, that's right.
We have those isentropic surfaces, right? That's what we need.
Yeah.
And theta will do what with height? Almost always. Theta will increase with height. Okay. So it says, consider an air parcel shaped like a block with dimensions delta x, delta y, delta z. So what I'm going to do here is I can create another. I've got this little block here, right? And the coordinates of this would be delta x, delta y, and here we're going to use delta p. So up and down is delta p. And remember that delta x is a distance in the zonal direction. Delta y is a distance in the meridional. Delta p is a vertical coordinate. Okay, so again, and this is what bothers me in math, because in math, do you agree that sometimes we take a square and we say this is x times y? We shouldn't be doing that. We should be doing delta x times delta y. That's what we should be saying. And we should teach students this from the beginning rather than say x and y, because I think it leads to problems. Do you guys agree with me on that?
Mm-hmm.
Yeah, I had a question here. How do you delineate delta from sigma there? Like, they almost look a little similar.
Delta is the, I guess that's the curly Q. Sigma is just a cross,
Sigma's a cross, delta's a curly. Got it.
right? Just goes, sigma is just that, whereas this is that. Do you see that, Jim?
Yeah.
Or James? Okay, so density is mass over volume. So the mass is density times the volume, and the volume of this is right? That's what they have there. And then, oops, no, I'm sorry, I lied. That is not what they have there, is it? They have this, because there is physical distance. So how did they go from that and get rid of this? So that it goes like this. How do they go from this to that?
What's that? What's the denominator? Is that a G or a?
Hey, Allison.
That's G.
Oh, now that Allison's here, I can make you all bigger.
Yeah, I'm only gonna be here for till 9:30. I gotta really quick go to my class for a bit, but I might pull it up on my phone.
Okay.
But I just did my soil presentation, so at least that's over with for the day.
How'd you do on that?
You said I did well, so.
Good. How's your grades all for everything else?
Oh, for everything else, I mean, I'm all at A's. I just want to keep them at A's.
You're amazing.
I just have dynamics on Wednesday or Thursday that I'm freaking out about, so hopefully this helps me.
Okay, we'll figure this out. So what we're doing is we're taking the hydrostatic, right? That's what this transformation is the hydrostatic. So we have, right, dP dz equals minus rho g. So we're just changing, instead of dP dz, we're making it a delta p and a delta z, and that's what we're doing. So we're basically taking the hydrostatic, if that makes sense to you. I mean, I want you to be able to see these kind of things. Okay, then they say because the mass of the block is not changing in time, right? And what do we call the block then? This column is a what block? It's a Vegas block, so there's no change in mass. What's in the box stays in the box. So we're saying, when I take this, the change in the mass with respect to time is d, and then I'm going to take negative delta x, delta y times delta p over g all over dt. But using the product rule, I know that the negative comes out because it's -1. That's a constant. And does a constant change over time? No. Do you understand that gravity doesn't change over time either? So I simplify this to going to just this. And we know that that change in mass is 0. Okay? Now what? Now what do we do? Well, now we're going to go up here to the top. Just erase that for a second, because I don't need all this. And over here, I'm going to now say, I'm going to expand it. So what I'm doing is I'm taking the what? I am taking the, what is the expanded form? How do I go from 7.38 to the next equation? That's just using the what? What's going on? What is that? What am I doing there?
It's product rule.
It's just a product rule, right? I'm taking out the derivative of A times B times C, in this case, is A times B times the derivative of C plus A times C plus times the derivative of B, etc. That's just the product rule. So I'm not going to write that all out, okay? Expanding the time rates of change in terms of the partial derivatives of the velocity components, as is the derivation of 7.2. It is readily shown that that is true. So I guess I need to write this out because we want to do the whole thing. This is what we did last week. Delta Y times delta P times plus delta X times delta P times the oops. Now it says the derivation in 7.2. So we go back to 7.2, which I believe is what we did last week, right? When we talked about what the divergence is with the areas, right? We did this last week, remember?
Yes.
So it says it's readily shown that we get, this is the U so we're going to say from last week. And I think I'm naming the, by the way, I'm naming the lectures based on what we're talking about. I think I'm starting to do that now. I should have done that all along, but I didn't think about that. Plus dV dy plus d omega d, oops, d omega dp. Now omega is dp dt. So I want you to understand something here, because I don't know. I don't think we may have to go back and get it. But we say that W is dz dt. Right? We said that from the beginning. And I don't know, I'm trying to think of what would be better. Would it be better if I did this? Is that better? If I use partial derivatives, might be more sensible. Right, we know that's the vertical velocity. Well, omega is the change in pressure with time. When air is ascending, okay,
That's a
That's a
question.
question.
that's the question. How does the height change with time? So you agree that as I go higher in time, then I must have ascending air. What does this mean? What would vertical velocity be? what would upward motion be?
That would be a negative quantity?
Do you agree that it would have to be negative in here?
Yeah.
Because upward motion is, so in other words, W and omega are opposites. Because one, the pressure is going down as you go higher. So there's an inverse relationship. So positive W is negative omega. So I want to show you, just so that you see some practical application to this. If I go to the models, okay, so let me go to the NAM, and let's go to 500 millibar vertical velocity. What we're looking at here is we said this over here in the positive numbers is vertical motion. Oh, that's really, we have a lot of clear air around here, don't we? These are all ascending motion. But notice that we say that it's at negative 20, or this is 24. But the velocity is in minus microbars per second. So remember, a microbar, we have millibars, that's 1,000th of a bar. So a microbar is 1,000th of a millibar, 10 to the minus 6. A microbar is about a centimeter per second. So 1 microbar is about 1 centimeter per second. You could do the calculations on things that we know. So notice that we are plotting them out to be positive, inferring that it's upward motion, but that's actually negative microbars per second. So this, we are plotting, what are we plotting on here? We're plotting omega. This is omega, little omega. Now keep in mind, something that's annoying, and I'm sorry, this is the case. Do you understand that this omega, this little omega, is vertical motion in terms of pressure versus time? But we've used omega somewhere else. We've talked about it. What else is little omega used for?
Is it in the Coriolis force?
That's capital omega. So little omega is rotational frequency. It is the angular momentum type term. We use capital omega when we talk about the Earth's rotational frequency. But little omega is rotational frequency. But in here, it's vertical velocity. So we're going to see two versions of omega. Just make sure that you are clear on which version of little omega that is. So when I go to this equation, I am now saying that this is your derivative. But we already said the other day that the complete three-dimensional derivative, assuming that there's no pressure, external pressure, or internal temperature changes, because it's a mass continuity. And even if this is warmer, do you understand that the mass is not changing in here? Mm-hmm. We say that equals 0. And what I can say is this, oops. Try it again. Is this. And the reason we can say that is we know that this is this.
They're equivalent?
Well, yeah, because this is a divergence term. These are all divergence terms. So this is horizontal divergence in this circle, right? Because we're ignoring the vertical part of this. We're putting it on the other side of the equation. So I'm saying del dot something, we say that's the divergence, right? Del dot a vector is the divergence of the vector. And I'm just saying the horizontal component of the velocity vector. And then that's what I'm saying that this is actually horizontal divergence. And then they show you a picture that kind of deals with this, but I don't even think that's a good picture. And then they go over here, look on the next page, 7.39b. That's what we have. Now here they say it's the divergence of the horizontal wind field, but I put an H in there so that you understand it's the divergence of the horizontal wind field. Okay, does everybody understand the mathematics of this so far? Now we're going to get into the meteorology of this, and it's going to be really, really awesome. You can read the next couple of paragraphs where they talk about upwelling and downwelling and Ekman spirals and Ekman drift and coastal upwelling. It's really cool that this is part of it. But what I want to do is I want to go to get to equation 7.4. So I'm going to take this.
Or 40.
I mean 7.40. I do that too often. I'm going to erase this. And I'm going to go to that equation. I'm going to draw it in here. I'm going to say dp dw, or d omega. Oh, God, what is wrong with me?
Dyslexia rears its ugly head.
I'm uplexia. D omega dp in partials. And we said that's the horizontal divergence. But what I'm going to do is I'm going to integrate this. So I'm saying, how does the vertical velocity, which is what omega is, change with respect to a pressure change? And the way that I'm going to want to be able to do this is I'm going to do this. I'm going to make a mathematical, this is not really legal. I'm going to bring it to the other side.
Don't forget the negative sign.
Thank you.
Mhm.
Okay. So I really am not allowed to break up a partial derivative like this. But this will eventually get omega, which I can now integrate from some reference P star to another P. I'm integrating from here to there, right? From a vertical distance coordinate system. I'm going to talk about how does the vertical velocity change from there to there. And so I'm going to integrate this side of the equation, put the negative sign out in front because I can. With respect to pressure. So instead of this, I'm going to use D. So technically, this is what it is, but what they've done is they say omega dp. And then this becomes dp. So they use the regular derivative as opposed to the partial derivative because we're neglecting any other variance in the vertical velocity horizontally negative. We're saying that the total change in the velocity, the way that we're interpreting it, doesn't worry about any other changes temporally or spatially, just in the vertical coordinate. That's why we can get away with that. And this will become, use my right color. This will become omega at some pressure minus omega at a standard pressure reference. And I guess I could have said the pressure at point A, pressure at point B, is equal to this side. Now, what should you be questioning on the right-hand side that I have not included?
Bounds of
The
integration.
boundaries on the integral?
Okay, what we call the limits of integration. So we're saying this is the divergence at a point. So you know what I think? I think I might show you this. This might be better. Instead of doing star, let me do the pressure at point A to the pressure at point B. And we are thinking about this in terms of this. I'll draw a little picture. And we're going to say this is the vertical velocity at point A and the vertical velocity at point B. So we're saying, what is the change in the vertical velocity from A to B? And so I'm going to say that that's from A to B, and that's the divergence, the horizontal divergence at point. So in other words, what is the horizontal divergence at a point from at point A to point B? So I'm integrating the net or the total divergence as I travel upward. That's what this is saying. Now, to do this, we have to do a little bit harder. So now we're going to integrate this for the entire atmosphere. And we're going to say, okay, omega at S. So go ahead, now let's go back. In this form, the continuity equation can be used to deduce the vertical velocity field from a knowledge of the horizontal wind field. A convenient level is the top of the atmosphere where P star equals 0 and omega equals 0. So what we're saying is, what this is saying is in my picture, letter B, omega equals 0.
And P equals 0.
Yes, although I don't really care. So it's really omega when P, the omega at P, which equals at B, something along those lines. Right? This is, the subscripts are just trying to clarify. So that's why at letter B, omega 0. So at the top of the atmosphere, there's no vertical motion. Well,
Pardon me.
integrating 7 to 40 downward from the top to the Earth's surface. So now we're going, at letter A is going to be the Earth's surface. We say that the vertical velocity at the surface is going to be equal to minus the vertical winds at the surface times the pressure at the gradient at the surface minus Ws dp dz minus
Oh, geez.
0 to the pressure at the surface. Oops, no, that's not what I want. dp. And so it says incorporating this result and 7.34.
What
Go
are
back,
these?
go back to 7.34.
What are the signs on the integration? Again?
0. So this is where the pressure is 0. So this is actually top of atmosphere. And that's surface.
That's PS.
Yes.
All right, thank you.
Now, in order to do this, we need to go back to equation or to page 291. So we have to look at pressure as a vertical coordinate. Okay, so I'm going to go back to page 291. I'm going out of order. So we go omega is defined as dp dt. And then I'm taking the derivative of this. Do you remember when I take the total derivative, I get the local pressure change plus the velocity times the gradient of the pressure. That's how the derivatives work. But I'm going to break it up into components. Plus W dp dz. So you need to remind yourself that this is the, what is that? What do we call what's in the circle? I'm sorry, guys. I'm not as focused today as I usually am.
Hydrostatic equation?
No, what? Do you remember total derivative? Total derivatives. So this is all about the total derivative. So what do you have about the total derivative? You have the time rate of change plus the what? What do we call this? What are these terms called?
Talking a primitive equation?
Is that the advection term?
Which is super cool, by the way.
That is the advection terms. Because, right, that's what I have over here. This is how you do a total derivative. It's the velocity. It's the velocity times the gradient of each zonal, meridional, and vertical system. So this is exactly the same thing that I'm doing here. Instead of temperature, I'm using pressure. The only difference is I am combining these two terms into the vertical width. Because in 3 dimensions, we would say that this becomes right? That's what we say. That's what this term is. But instead of doing it as a 3-dimensional vector, I'm going to take only the middle 2 terms, right? Those middle 2 terms and the final terms separately. So that's what I've done over here. Now over here, what they say is that if omega is this, I know what dp dz is from the hydrostatic equation. So I'm going to go, whoops, with yellow. I'm going to go with omega is equal to the change in the pressure over time plus the horizontal divergence or wind field times the gradient of the pressure, horizontal pressure gradient, in other words, plus minus rho g omega. No, not omega, W. This is a W.
Plus the negative rho g omega.
Yeah, because remember, dp dz equals minus rho g. Right? So all I've done is I've taken this and I've substituted to minus rho g. Again, pointing out that this and this are related with the negative sign. You see that? You think you need to know the hydrostatic equation like this all the time? You need to be thinking hydrostatic always.
Paul, could you move your Epic Pen
Yes, I can.
menu? It's step, there you go.
There we go. And what they do is they sit here and they go, okay, well, omega is approximately equal to minus rho g w. So how does the book get this equation from that equation? From this equation. What happens? How do we do this? What are we saying about these two terms? What are we doing to go from here to here? Give me the word.
Is it that they're negligible because they're orders of magnitude smaller?
And what do we call that process? What are we doing to the equations? And yes, your answer is perfectly right. But what's the word that we call that?
I know it's on the tip of my tongue and I just can't remember it.
Say what you said again so everybody hears you, Allison.
Because it's orders of magnitude smaller, they're negligible. So
What's that called? Nick?
scaling?
Yes. So they're scaling this equation. And so these two terms are orders of magnitude less, and so we're neglecting them. So what does that mean? Well, it says, okay, look at the thing they say. Typical local time rates of change of pressure in extratropical weather systems. If so, in other words, how does the pressure change over time? Well, how does it change over time? And they're saying, well, if you were in the extratropics and you had a 10 millibar change of pressure in a day, then that scales to 10 millibars per day. The horizontal advection of pressure, which only comes from what? Here, let's see if you guys can reason this one out. What does the horizontal change in pressure come from? The advection of pressure. You guys have no idea what I'm talking about, do you?
No.
Okay, imagine this. Imagine those are isotherms. What does the wind have to do for them to be advected?
Cross them.
It has
Perpendicular?
to cross it, right? If they're crossing them, you're going to advect temperature. Okay? So let's forget about those being isotherms, and let's just say that they are isobars.
Okay.
So how does pressure get advected? The wind has to cross the isobars.
Isobars.
But in the upper atmosphere, how does the wind blow?
Geostrophic?
Geostrophically. Geostrophic winds do not cause advection of pressure. So it's only the ageostrophic wind, only the deviations off of geostrophic. So when you look at this term is even less than 10 millibars a day, much smaller. Now you could do that by saying, all right, let's do an example of one. Let's take a look at something. How fast are the winds aloft? Let's go, just for the hell of it, 20 meters per second. That's the wind. That's 40 knots. Okay? What is the horizontal pressure gradient? Would you agree that it would be 4 millibars? Over what distance? How far does it take in the exotropics to drop 4 millibars? Can we say 100 kilometers?
$80. Okay.
Okay, so what does this become? 20 times 4 is 80. So it's 80 divided by 1 times 10 to the 5th. And then what's the unit? This is millibars per second. So I need to multiply by 3,600 seconds per hour times 24 hours per day. So somebody do this calculation. 80 times 3,600 times 24. Divided by 1 times 10 to the 5th. What do you get?
$69.12.
Millibars per day. That seems like a big number, doesn't it? But that's assuming that this is geostrophic. So you would have to take the percentage of the air that's ageostrophic, which is going to be way smaller. At least 10 times smaller. So this will go to about
6.9.
Well, that's under 10 millibars per day. Then the question is, well, what's this? Gravity is 10. Vertical motions are, so this would be density. So we're going to say density scales to about 1 kilogram per meter squared. Gravity scales to 10. And W, we said, is on centimeter per second. Well, convert this into centimeter or meters per day. So W is 10 centimeters per second times 3,600 seconds per hour times 24 hours per day. But we need to get rid of 10 centimeters, which is actually 0.1 meters. No, point. A centimeter is 100th of a meter, right? So 10 centimeters is 0.1 meters.
Right.
So take 3,600 times 24 times 0.1. What do you get?
8640.
How much?
8640.
Times 0.10. 0.1.
8640.
Is it really that much?
Yeah, because 3,600 times 0.1 is 360 times 24.
Oh. So that's a lot. If you let a parcel And think about this, right? If you let a parcel go through the atmosphere at 1 centimeter per second, how long does it take to go through the entire atmosphere? Let's go through the troposphere. Let's say 10 kilometers. At 1 centimeter per second, how many seconds does it take to go 10 kilometers?
It's around 10,000 seconds, or am I doing?
Divided by 3,600, that's a couple of hours. So in other words, air can travel through the entire troposphere in several hours. If you were in a thunderstorm, which by the way is non-hydrostatic, how fast can air go through the troposphere?
A lot faster.
15 minutes, right? So synoptic scale motions are slow, but over the course of a day, it can travel a long way. Air can go really far if that's the case. So this term is way bigger than these other terms. And that's why to within 10%, this is true. Now, let's look at the next page, 291, top of the on the right column. I mean. Within the lowest 1 to 2 kilometers of the atmosphere, where W and omega are constrained to be small due to the presence of lower boundary, the smaller terms in 2.32 cannot be neglected. At the Earth's surface, the geometric vertical velocity is that the vertical motion at the surface is the velocity times the height gradient, or the height of the terrain. So you're getting motions because the terrain changes. That's basically what they're saying. So now I want to go back to page 294 and take a look at this information. And what we get is we go back to, oh my God, where is it? This top term. Okay, so I'm going to do this with an eraser. I'm going to get rid of all this so that it's a little bit cleaner. Okay, just going to get rid of all that. And now I'm looking at this formula. At the Earth's surface, the pressure tendency term, which is which guy? I've lost where we are from what we did before. When did I switch over to page 291? I said it right there. So where did this come from? I'm sorry, guys.
We went back when we were working on 740, getting to 741.
So the Margulis pressure tendency equation is going to be this. That was a really thick letter.
Did you say this was the Margulis?
Yes. Okay, so that's this equation, right? The vertical velocity at the surface, which is the change in pressure over time. So do you agree that when the pressure changes over time, that's called tendency, pressure tendency? Minus Ws dp dz minus this last term. So it says the order is 10 millibars per day. That's what we tend to see. And the advection and the vertical velocities are even smaller. It follows that the divergence is about 10 millibars a day. So then they say based on these numbers that we plug into there, we get 10 to the minus 7 per second. So divergence, right? They're calling this term over here, they're calling that term the mass-weighted vertically averaged divergence. So I'm integrating this. And again, I don't know how to integrate it like mathematically. That's a really hard function to do. I'm just saying this is what I do, and I'll show you in a minute. It's really important that you see this. So we say that that is about 10 to the minus 7. So 10 to the minus 7, s to the minus 1. That's the unit of frequency, that's the unit of divergence. All of these things are the units of that. So take a look at the next page. That the vertically averaged divergence is typically about an order of magnitude smaller than typical magnitudes of divergence observed at specific levels in the atmosphere, reflects the tendency, first pointed out by Dines' conservation principle, for compensation, the Dines compensation principle between lower tropospheric convergence and upper tropospheric divergence and vice versa. It says vertical velocity, which is the vertical integral of the divergence, tends to be strongest in the mid-troposphere where the divergence changes sign. Now, this is mathematically very difficult. So what I'm going to show you is how to interpret it much easier with what my students have called the DNA chart. So I'm going to start with this. I'm going to have a little vertical chart right there, okay? And I'm going to call this, which one's that one? But I'm also going to reference this as the vertical velocity. Now, the divergence, which I will color in dark blue, might look something like this. So what am I saying? And this is height. What am I saying is true at the surface? What is the air doing?
Converging.
You've got convergence at the surface. What's it doing aloft? Divergence. So my vertical velocity, which has to, what is the vertical velocity at the ground?
Pointing up.
No. The vertical velocity at the ground must be 0. Now, you can't dig a hole.
Oh, yeah.
So I have vertical velocity. Now, if you think about this equation, I'm saying that with convergence, what will the vertical velocity do? It will go, I will increase, I will accelerate up until where? What is this called? What is the level called? What's that stand for?
Level of no divergence.
The level of non-divergence. So what I'm saying is that the vertical velocity is maximum at the LND. Now, remember, I am summing up the divergence. So what starts happening here is I've got convergence up to a level. Now the air starts to diverge. What will that mean to the change in the vertical velocity if the air starts to diverge? What will the vertical velocity do? The vertical velocity field will start to decrease. What is the vertical velocity there? Zero,
0, yeah.
right? Listen to me, watch this. I am summing up the convergence. Summing up is finding areas underneath curves.
Right.
So in essence, what I'm saying is that when I sum something up, I am taking a look at that area. Actually, it might be better if I do this. And then what's this area going to be? What I'm saying
It
is
should be equivalent.
when this area is equal to this area, then what would be true? The vertical velocity is 0. So in order to do this, I am summing up and integrating the convergence. If you go back to that original column, I'm taking convergence. Can I have convergence all the way up?
No.
Right? I can only have so much convergence before I start to have divergence. That is known as Dyne's principle. So let's do this for a second. Dyne's compensation principle. Oh, PAL. I always get that wrong. So let's take a look at this. In meteorology, Dyne's compensation states that net mass convergence into a given column of air must be balanced by net mass divergence from the same column of air. The implication is that rising air in the atmosphere must be balanced by sinking or subsiding air. Dyne's compensation applies especially in mesoscale circulations and in macroscale circulations. It is not uncommon to see anticyclonic cirrus outflow from a hurricane in visible satellite imagery. Okay, so that's this. And I probably should spell this correctly. Wait, is it principal LE or AL?
I thought LE, because PAL,
It's your path.
right. That's how I remember it.
Okay. Then that was right the first time. So, at the level of non-divergence should be your maximum vertical velocity. You know what I need? I need to get some fresh coffee. Give me 30 seconds. Do you mind?
Not at all.
I just want to pause. Okay, we're back. So going back to this diagram, does this diagram make sense to you? Because I'm having a hard time. You're not really giving me any feedback. Are you understanding what I'm talking about?
Is LND shown on a chart somewhere?
No,
Okay.
but mid-latitudes, LND is around 500 millibars. Why do you think we look at the 500 millibar chart all the time? It's usually about the LND. In the tropics, where is it?
Lower?
About 400 millibars. So what does this eventually have to do? The vertical velocity at the top of the atmosphere needs to go away. It needs to go to zero. So I need to compensate for that. So eventually I'm going to have a boundary of vertical velocity. Because it has to go back to zero at the top of the atmosphere. So the total amount of convergence and divergence must be zero, because I only get vertical velocities. Like in this case, what is going to happen to the vertical velocity field past this point? If I continue to have more and more divergence, right? Look what's happening. Do you see how much divergence there is along? What's the air doing above this yellow line?
Spreading out? Spreading out?
No. Vertically.
Accelerating?
Oh,
It's got to be sinking.
sinking,
What's it doing all up through here? It's rising.
rising.
Its maximum at the LND. So here's the weird part. If I have a jet stream that's strongly difluent, or let's just go crazy, let's go strongly divergent, is that good for thunderstorms?
Yes.
Yes.
Not really. Because what happens is the air is so strongly divergent. Look what's happening. You actually have sinking air
Okay.
at high levels. What does sinking air do in terms of
Stabilizes the
it
environment.
stabilizes the air. So this is where you get what's known as a Cape robber. Strong upper level divergence can actually cause the air to sink. So what do I want air to do? I want the vertical velocity to be strong, right? In a thunderstorm, or let's do it this way. In a capped environment, about 700 millibars, the temperature is too warm. So I want that air to destabilize. I want the air to rise a lot at 700 millibars. So let's just say, for the hell of it, that I want the air to rise in this area. I want rising air here. How do I get the most rising air? What will cause the vertical velocities to increase?
Does that say at 700 millibars too warm?
Yeah, so I'm saying it's a capped environment. I'm saying it's too warm. So I want the air to rise. I need, in other words, strong vertical motions. So what causes, in this diagram, the vertical motion to go faster at this dot? What do you think, Mr. Norris? This is a hard question.
Okay, repeat the question.
I am looking at this green dot. I'm
Right.
saying that's around 700 millibars. I have an atmosphere that's capped. And the only way to break a cap is for air to go up.
Right.
How do I get the air to go up stronger at the green dot? Jacob or Nick, what do you
By
think?
going.
What are you thinking? Jacob? Are you there, Jacob?
By increasing convergence?
Yeah, in the bottom.
Right? Okay, so now you're thinking, right? Because the vertical velocity at a point is the sum of the horizontal divergence from the ground up to that point.
So you want a fatter curve underneath that point.
So, right, so what I would do is I would sit there and go, well, wait a second, what I'm really looking for is to get my vertical velocity here to be more. I need to get more convergence. The more convergence, then the vertical velocity field will go up faster. My vertical velocity field is the summation of the entire convergence up to the LND. So that will still maximize at the LND. But do you understand that more divergence aloft doesn't make that happen? More divergence aloft will do what?
Cape robber.
Cape robber. The low level wind field 700 millibars is only a result of the amount of low-level convergence, not the upper-level divergence. Synoptically, upper-level divergence, well, that's fine, because I know that I'll have an LND someplace. I know that there's convergence to compensate for that. But too much is bad. I want maximized surface convergence. The more convergence down low, the better it is. That's why I'm going to get thunderstorms forming when I've got fronts and dry lines and stuff like that, because that's where my surface convergence is maximized. So when I look at mass divergence or surface convergence or moisture flux divergence, which are parameters we have on our satellite page, I'm looking at bullseyes, because the more convergence, the greater the ascent. The greater the ascent, the greater the destabilization. The greater the destabilization, especially in a capped environment, the more likely I can break that cap. But it's all about what's going down, up, not up, down. So this is super important that you understand this concept. Now,
Okay, question.
yeah,
Let's take a situation where you've got good, where the green part is significantly less. Does that imply that the LND will also go up or go down?
if I have more what?
In the case of a favorable convective environment. So the green area would be less, right?
Yeah, I mean,
And the LND would be lower?
the LND would be higher. No.
Okay. The LND marks the area where the green,
The LND
the area
wouldn't
of the,
matter. The LND wouldn't matter. The
oh,
location of it.
Okay.
Because if I had less divergence aloft, it just says that I'm going to eventually have to have more divergence for a while
Okay. Okay.
before I start to reverse the vertical velocity. So less divergence will eliminate the K problem. So let's look at some soundings of this, which we have on our model. So unfortunately, we're at that time of the year where well, I guess I can look at a sounding here, maybe. Okay, and what we're looking at here is these little lines here are your convergence and divergence, or omegas. So here we have, it says omega plus omega, which is what? Positive omega is what?
Divergence.
No, omega.
Rotation.
No. Positive omega. Remember, omega is vertical velocity.
Yes.
Positive omega is sinking air. Negative omega is rising air. So over here, I've got a little bit of rising air. That's not very good. That's not a great example of this. Here. Somewhere down there. All right, so that's. Let me just go here. So in this shower where I've picked this point, where's the rising air maximized? Here. What's happening down low? The air's sinking. So I'm in a, this is probably updraft over here, and this is downdraft. So, you know, again, you can interpret some of these things by looking at the vertical velocity field. So I know that I've got sinking air down low, which means what's the surface field? If I've got sinking air to start, what must be the surface field? Notice I've got convergence, which is ascending air. So if I have this reversed, if I have a field like this, there must be divergence down low, right? So I have divergence. If I'm divergence, where am I? I'm in the cold pool of a thunderstorm. I'm in the downdraft. So let's see if I can get something a little bit more interesting. I wish we were in convective season. It'd be easier to show you some of this stuff. Here, we're a lot closer, right? Because we've got strong vertical motions throughout a deeper layer of the atmosphere. Little bit of divergence here. So there's, again, this is a convective allowing model. So whenever we get a downdraft, whenever we get rain, we have a little divergence at the surface. When we go to the satellite page, just so you know, I can do an overlay. And on here, I can give you moisture divergence or just mass divergence. So in here, there's strong convergence down here. There's some convergence down there. There's some convergence at the surface. Let's see what the plots are. Why is there convergence here? So we have convergence here at the center of this guy. So let's take a look at a model. Sector view in the northern Great Plains. Is this making sense to you?
Mm-hmm.
So here I've got convergence, or I've got ascent, which means that I've got convergence. Does that make sense?
Mm-hmm.
I mean, that's got to be the case. Cold, this is not certainly convective allowing. Ooh, this is interesting. Good. Look at the wind shear on this thing. It'd be awesome. Let's go back to the satellite and let's find some divergence. Well, there's surface divergence where? Well, let's go to Galena. So let's go to the mid.
I suppose we could check that windstorm from the other day.
I don't have the soundings. We don't keep them very long. It's a lot of them.
Drat.
Okay, so here my vertical velocity field is sinking, which is where there must be divergence. So are you getting the idea of why I would use fields like this in convective analysis? Because the more the convergence, the more the air must be ascending at low levels. it's the surface field that matters the most. Now, let's go to page 295 and finish up. So do you have any questions or comments on the stuff that we've done today?
Nah.
What do you think, Allison? Are you there? Are you walking or?
I'm here. I'm trying to still wrap my brain around it. I'm gonna have to rewatch the.
Are you doing any of this in Dynamics yet?
So we're doing the math part that you're doing. I think we're doing that kind of stuff a little bit. We're more so doing like streamlines, trajectories, and I'm guessing it'll lead to what we're doing here. So that's why I'm trying to fully process it because I know I'm gonna need it.
Okay. Did you get the stuff? Did you go look at the tapes that we did of streamlines and trajectories last week?
Yeah, because I was here for like half of it, and I'm rewatching the one that you're doing about that. So yeah.
Okay, Nick, on page 294, it is instructive. Can you read that?
What did you say?
295, first column, second paragraph.
Oh, 295, first column. It is instructive to consider the vertical profile of the atmospheric divergence in light of the idealized flow patterns for a two-dimensional flow in two different kinds of waves in a stably stratified liquid in which density decreases with height. Figure 7.20a shows an idealized external wave in which divergence is independent of height and vertical velocity increases linearly with height from 0 at the bottom to a maximum at the free surface of the liquid.
So here they're saying, on figure A, they've got ascent, right? And notice that everything is converging in this wave. And the wave amplifies as you go higher. And you've got convergence all the way up, which means the air will accelerate. But that should make sense because if a wave is coming through, right, you have the top of the wave is going to be pushing up. So the net convergence will cause the top boundary condition to be upwards of this, what we call free surface wave, or the external wave. In figure 720, it shows an internal wave that's bounded by an upper level ridge, a rigid upper level lid, so that W at both top and bottom is 0, requiring perfect compensation, right? So this is where we get to the Dyne's compensation principle, is we have the boundaries, top and bottom, are both vertical velocities of 0. And the first one, in letter A, the top vertical velocity is not 0. In B, the top vertical velocity is 0. So if I have this area of convergence all the way up, the air will eventually have to stop and the air is divergent along. So I have convergence at low levels, divergence in upper levels, and I get circulations. In the Earth's atmosphere, motions that resemble the internal wave contain several orders of magnitude more kinetic energy than those resembling the external wave. So in other words, the majority of the motions of the atmosphere are coming along as these internal waves with rigid boundary conditions, with air that's not expanding and going out. Those are waves. So what we're saying is that what matters is the top boundary condition. Obviously, the bottom boundary condition, being 0 vertical velocity, is necessary because you have the ground. You're not digging holes into the ground. The air is not even digging holes into the water, into the ocean. But at the top of the atmosphere, you could get an external wave that's going to expand the atmosphere up and down and push the atmosphere higher. So you can get these waves. But the majority of motions in the atmosphere are going to be rigid. They're going to be internal waves. And that's what's happening in letter B. And that's where convergence and divergence, and the Dines compensation principle matters. So when I say mass continuity, a level of convergence must be associated with the level of divergence and vertical motion in between. The only difference between what I'm telling you today versus what I've told you in the past is that the vertical field is not just air rising, it's actually accelerating. That you get changes in the vertical velocity. So that's going to be super important that you kind of understand these pages. Now, I think these pages are some of the hardest pages in the book. And I want you to be thinking about this. There's some really good stuff here. By the way, in a hurricane, do you remember what's the key of a hurricane according to Emmanuel? We said we need a warm core, right? We need the warm core of the hurricane.
Mhm.
What's the problem? Well, the LND is way up high, which means what is the air doing all the way up?
Converging.
It's converging. It's not, it's doing this for a while. Eventually, you'll have divergence. So our vertical velocity is maximized at the LND. Vorticity is also that's where the spin changes directions. So you have cyclonic curvature into the LND, now all the motion is up, and now it anticyclonically diverges from the top of the hurricane. So that's Dines compensation principle. The other thing that's important is if you're going to maintain the warm core, what's the air like up here around 500 millibars? It's very dry in the tropics. So this really dry air can be entrained into the core of the hurricane that causes evaporation, that causes cooling, and I destroy the warm core. So I lose my clouds whenever I'm entraining dry air. So I have to be very careful about, I need that large area of not so dry air that doesn't get pulled in because there's convergence for a while. And that hopefully that makes sense. So that's why that's why it matters to keep that warm core. I can't go over dry because then that just erases all my thunderstorms. Okay, that's kind of a funky, that's a funky lecture today. But I think it's kind of cool. What do you think, guys?
We'll have to take in.
Mhm.
A lot to take in. So on Thursday, we're going to go back. And on Thursday, we're going to do the dynamics of horizontal flow, which is page 276. Have you been doing that, Allison? Have you been doing Coriolis force? And
Yeah, we're getting to the Coriolis force and centrifugal force.
Who's teaching that course?
His name is Dr. Epitiano. You would actually like him. He's pretty funny.
Okay, cool.
He's allowing us, so he does this funny thing where he was doing eraser noises when he would erase the board, and now it's turned into this thing where I made a joke one day where I played like a heavy metal song while he was doing it because he was asking for elevator music, and I did like a punk song. And then now it's turned into every day when we go into class, each of us have a song that we play. And like, I've played like Let It Go, and we've played like old like cartoon songs, like the title like MASH theme song, and like we played like Jeopardy, and so it's like, yeah, so it's pretty fun.
Well, we'll go through pages 276. One of my favorite things ever is the derivation of the Coriolis force. It's going to be the most awesome, cool, challenging, way awesome thing ever. I love this section. This Coriolis force derivation is one of the funnest things. Why is it 2 omega v sine phi? So it's going to take some good drawing. I'm kind of challenged by it, but we'll see what we can do. So
When is your guys' end of semester?
December 13th.
Oh, cool. Yeah,
So
I'm
right
coming
now-
home. I'll be home next week.
Oh, good.
I'm
Oh,
staying.
you for good?
Yeah.
Oh,
Yeah, I heard a lot of universities are just ending at Thanksgiving instead of like.
Yeah, I just have my finals like after Thanksgiving, but they're all online. And
Oh yeah, that
it's
too.
like the week after, but I'm done by like the 4th.
jeez. Well, enjoy your time, guys. I will see you all on Thursday.
Yippers.
Yep.
Peace
See you
out.
on Thursday, Chief.
Bye-bye.
Bye.